In this problem, we have an opportunity to calculate the change of length of a cable that gets stretched with a certain amount of axial strain using this linear elastic, perfectly plastic model for the material. So to get started, there are only a couple of numbers that are given here. We have a length of a cable, which is 3 meters, and we have that we've, I guess, put this cable under a linear strain, a max linear strain of 0.17%. Okay, so let's just write that down, that the applied strain at this point, or the maximum applied strain that we have, is going to be 0.17%. And where does that go? That goes here between 0.1% and 0.2% on our stress strain curve for the material in this cable. Well, if this point were over here in the elastic regime, right, and we were to let go, okay, which is what we're talking about, says once the person releases the acrylic sheet, meaning so the cable's supporting this acrylic sheet, and this comes from a prior problem that we've looked at in previous assignments. But once we let go, if we were here and we were to release the load, right, we just go back to zero. But since we're in the plastic regime, we know that something else is going to happen instead, okay? Because we are beyond what the um, yield strain is. Okay, the yield strain is 0.1% here. This is where we go plastic, where you hit the yield strength. So if you unload after you've gone plastic, you will have the return along the slope of your elastic modulus. Now, in this case, we could attempt to calculate the elastic modulus in a quantitative way if we knew what Sy was, and if we knew what point the yield strain is, and we do know that, but we don't know what the yield strength is. But we do know that the linear regime only went 0.1%. Okay, well, maybe not only, but it goes 0.1%. Okay, so that means that we're going to go back the same amount that we went when we to go plastic. So that's going to be the 0.1% going backwards. So you see, I've kind of drawn it sloping this way, and I essentially know that my residual strain, which is described by this distance here, is going to be the epsilon max, so that's the 0.17%, minus the yield strain of 0.1%. Okay, hopefully you can kind of see that. So now we get that the residual strain is 0.07%. That's not what the question is asking. The question is asking us to describe the change in length of the cable, or cables, because there are a couple of them here, in units of millimeters. So in that case, we have a strain and we have an initial length of the cable. We can go ahead and go back to our definition of axial strain, which is going to be delta over L. Rearrange things, the delta is going to be epsilon L. And then we plug in the numbers. We have 0.07%, and we have 3 meters as the length. And it's kind of, I write it kind of weird. I don't think you would see this normally, but 3 times 7 is 21, right? So this is now 0.21 kind of percent meters. That's not a real unit. So I better move the decimal place over to the left a couple times. So I get 0.0021 meters, but we want the answer in units of millimeters. So we know that there are 1,000 millimeters in a meter, and so we multiply by 1,000 and we get 2.1 meters. Okay? Anyway, I hope that you found this example helpful in terms of being able to think about the residual strain that we get in a system based on actually an incomplete stress strain curve, but using some deductive reasoning there for what the strain associated with the yielding might be and how that influences how far back on this axis we're going to move when we calculate the residual strain. Thank you.